today this lecture will focus on limits from an algebraic viewpoint. That means we use algebra to simplify limits and define them to evaluate limits. But before we start, let me remind you of what we covered last time. We covered continuity, and let's solve one problem. Here we want to study continuity of the function g of x as x at the point x equals 1. And g of x is given by it's a piecewise function. That means it's defined by more than one rule, the first rule and the second rule. As we can see, g of x is 1 minus x if the values of x are less than or equal to 1, and it's equal to x minus 1 if the values of x are greater than 1. Now we want to study continuity of the function g of x, and let me remind you of we say that the function is continuous is that g of 1 plus 1 here exhausts some value. As we can see, x equals 1. We have equality here at 1, so we plug in 1 minus 1, which is 0. Find value. Second condition is that limit does exist as x approaches. Now, when x is approaching from the right, that is greater than 1. That means so x minus 1, which is 1 minus 1, that's equal to 0. Now we find limit of the function g of x as x approaches 1 from the left. From the left, that means x is less than 1, and here that means we substitute into the first rule. So we have limit x goes to 1 from the left, 1 minus x, plug 1, we get 1 minus 1, 0. The limit from the left equals the limit from the right. That means limit does exist and it's equal to that value. It's equal to 0. The third condition is that the limit at 1, or the value of the function evaluated at the point under study, is equal to the limit as x goes to 1. Covered last time. Now we will start a new topic. We study limits. We first study at infinity. That means we want to study the behavior of the function as x goes to plus infinity or x goes to negative infinity. What happens to the function? Okay. Here we'll focus on finding that limit algebraically. So look at the first example. We want to find limit as x approaches infinity of this function. This is a polynomial, and this is polynomial. What do we mean by polynomial? Let me remind you. Polynomial, for example, p of x is a polynomial if it can be written as a sub n minus 1 x to the power, a sub n n minus 1 x to the power n minus 1 up to 1 x plus constant term. This is polynomial because it can be written in this form, this expanded form, and n is non-negative integer. What does that mean? That means n cannot be negative value, for example negative 1, and it cannot be fraction like 1/2. Similarly, q of x is a polynomial. Q of x, let's say that the denominator is q of x. This is another polynomial. Let's call it b sub m x to the m plus b sub m minus 1, just to distinguish between p and q. Those are two polynomials. And coefficients can be different. Coefficients are the a's and the b's. X to n minus 1. Now we are interested in all the we have e of x. Now we have three cases. One is leading terms. I mean by leading term, this term. The leading term that involves x with the highest power n. And here similarly, x with the highest power here is n. So this is called leading term. Okay, so if we have three cases, the first case is that if degree of p is less than q, degree of the ratio, the leading and this is leading coefficient. Leading coefficient of so this number is the degree of q of x. Now we keep this in mind and we study the limit of this function. Now expression. Now look at the numerators, the denominators. That means the degrees are equal in the second case. And here we just take the coefficient of x squared in the numerator and the coefficient of x squared in the denominator, and that's equal. So that's the value of the limit. Let's do the second problem. Second problem, we have limit x goes to negative infinity of negative x squared over x. Degree of the numerator is 2 and degree of the denominator is 2. And in this case, we have same degree for numerator and degree of the as you can see here, x goes to infinity, but we still can apply the same. Now let's look at the third problem. In this case, degree of the numerator is 3, degree of the denominator is 2. As you can see, degree of the numerator is greater than degree of the denominator. That means that's the third case. Now we have negative infinity, because here we have negative. Now if you want me to show you how we get these numbers and how we apply these, from where we get these answers or these rules, we can apply the following method. If you want to find the limit in this example 3, you divide each term by x with the highest power from the denominator. X with the highest power in the denominator is x squared. That's x with the highest power from the denominator. Now we divide each term by that. And then we can simplify. We can divide x cubed by x squared. We are left with x, so negative x minus. Now here we divide 4x by x squared, and that gives 4 over x. And from the denominator, we have 2 minus 1 over x squared. Now after simplifying, we just plug infinity. We have negative infinity minus 4 over infinity, which is 0 in this case because we have limit, over 2 minus 1 over infinity, which is 0. So we get negative infinity over 2, and that's negative infinity. And that's what we obtained here. So that's the idea. Instead of writing all these steps, we can just use those rules. Now let's do problem 4. For problem 4, we have x goes to infinity and we have polynomial of degree 2 from the numerator and degree 3 from the denominator. If degree of the numerator is less than degree of the denominator, the answer is 0. If you want to check, let's use that method here, discussed here. So we divide with x with the highest power from the denominator. X with the highest power from the denominator is x cubed. So we have limit x goes to infinity of 2x squared over x cubed minus 4x over x cubed over 5x cubed over x cubed minus 3x over x cubed plus 5 over x cubed. And then we simplify. We cancel x squared with x squared from the denominator. We get x in the denominator here. So this is 2 over x minus, now 4x over x cubed is 4 over x squared. And then in the denominator we have 5 minus 3x over x cubed, that's 3 over x squared, plus 5 over x cubed. And then we just substitute infinity. We get 2 over infinity is 0. Any number over infinity is 0, especially if we're talking about limits, expression inside limits. Now 4 over infinity is 0. From the denominator we have 5 minus, this is 0 because infinity is in the denominator, plus 0. And that gives 0 over 5, which is equal to 0. As we can see here, we got 0 by applying the rule or by applying this algebraic method. Now let's do problem 5. As you can see, degree of the numerator is 2, degree of the denominator is 2, and the coefficients are 2 and 1. 2 over 1 is 2. Now sometimes we have expressions like this. We have square root. What should we do in this case? So in this case, it's better to divide by x with the highest power from the denominator. Or if you want to apply the rules, what should we do? We do the following. We just pay attention to the leading term from the numerator. What is the leading term? It's 25x to the 6th. So we write square root of 25x to the power 6 because that's the active term. Actually, that term determines the behavior. Now from the denominator we have 2x cubed minus 1. And then we can, as we can see, we can simplify the numerator. We have limit x goes to infinity. What is square root of 25? It's 5. What's square root of x to the 6? Square root x to the 6 is x to, now we can write this without using the square root notation. So the inner power is 6. And the outer power, which is the index of the square root, it's 2. 6 over 2 is 3. So we have 5x cubed over 2x cubed minus 1. Actually, we don't need negative 1. We can just pay attention to the x with the highest power, I mean the leading term. From the denominator, we don't need to pay attention to negative 1. So the negative 1 will not affect anything. So this is x cubed. Now, as you can see, the power is the same, so we just pay attention to the coefficients 5 and 2, 5 over 2, and that's it. Now let's do this problem, problem 7. Now for this problem we just plug, this is not a polynomial, we just plug the limit. So we have x goes to negative infinity, the value of the limit, e to negative infinity minus 1. That's 60 over, what is e to negative infinity? E to negative infinity can be written as, if you bring this down to the denominator, it becomes positive infinity, and we can put 1 in the numerator. If you remember, when we have, for example, x to negative 1, you can write it as 1 over x to positive 1. If we bring the power, the expression down, the power becomes, we change the power, we just change the sign of the power. So 1 over e to the infinity is 1 over infinity. E to the infinity is infinity. That e is a number. It's about 2.78 something. So 718. And then that number, if you, let's just consider 2.7. Now, if that's approximation, let's say, and then when you multiply this by itself infinitely many times, then you get infinity. So 1 over infinity is 0. So this is 0 minus 1, which is negative 60. Okay. Now the problem 8, we have infinity. We don't have a polynomial, so we just plug that value, infinity. So we have 2 to 3 times infinity over 1 plus 15 e to negative infinity. And we know that e negative infinity goes to 0, or we can write it 0. So we have 2 to the power infinity, which is infinity over 1, and that's infinity. Now, finding limits algebraically. How to find limits algebraically? Algebraically, we can simplify the expression and then plug the value of the limit. For example, here, for x squared plus 1 over x, the first step is to plug the value of the limit. Let's plug negative 1. We get 4 times negative 1 squared plus 1 over negative 1. And that's 4 plus 1 over negative 1. This is negative 5. And that's it. That's a number. Now, for the second problem, we plug 1. So we get 1 minus 2 over 1 plus 1, which is negative 1/2. The third problem, we plug 0. We get 0 over 0. And here, this is not a final answer. What should we do in this case? If we get 0 over 0, we need to do some algebra here to simplify. So we have x squared over, we can take x from the denominator as a common factor, and we are left with 1 plus x. And then we cancel this with this. We get limit x goes to 0, x over 1 plus x. Now we substitute 0. We get 0 over 1 plus 0, which is equal to 0. And that's a final answer. 0 is a final answer, but 0 over 0 is not a final answer. Now let's do the problem 4. Let's plug 1. We get 1 minus 2 plus 1 over 1 minus 1, which is 0 over 0. So that's not a final answer. We need to simplify. Let's simplify the numerator. By factoring the numerator, we have x minus 1 times x plus x minus 1. That's how we factor the numerator. What about the denominator? We have x we can take x as a common factor. We are left with x minus 1. And then we simplify. We can cancel x minus 1 from numerator and denominator, and we get limit x minus 1 over x as x goes to 1. Now, plugging x equals 1, we get 1 minus 1 over 1, which is 0 over 1, and that's equal to 0. Problem 5. Here we plug 2. 2 cubed minus 8 over 2 minus 2. 2 cubed is 8, so 8 minus 8 is 0 over 0, and that means that's not a final answer. So we need to simplify. Let's factor the numerator. How to factor cube of difference of two cubes? So we write, what is x cube root of x cubed? It's x minus what's cube root of 8? It's 2. And in the second parenthesis we write square of the first plus the first times the second, 2x, plus the second squared, 4, over the denominator is x minus 2, and then we simplify x minus 2 with x minus 2, and then we plug x equals 2. We have 2 squared plus 2 times 2 plus 4, and that's 4 plus 4 plus 4, which is 12. Now let's do problem 6. Here's same thing. When we substitute negative 1, we get negative. Okay, so here we have, let's make this negative 2 instead of negative 1, because if it's negative 1, we can get an answer. So let's do it as negative 2. So negative 2 cubed plus 8 over negative 2 squared plus 3 times negative 2. Let's see what we get here. Here we have negative 8 plus 8, and in the denominator this is 4. This is negative 6 plus 2, and that's 0. So 0 over 0, so we need to simplify. Let's simplify this. So we need, as we did for the previous example, we can factor the sum of the two cubed as x plus 2. This is cube root of the first plus cube root of the second, times, in the long parentheses, we write square of the first, Now we change the sign, minus the first times the second, 2x, plus the second squared, over the denominator. Now we need to factor the denominator. So we have x plus 2 and x plus 1. As you can see, 2 times 1 is 2, and 2 plus 1 is the middle term, 3. Now we simplify. We cancel x plus 2 with x plus 2, and then we plug the value of the limit. So we have negative 2 squared minus 2 times negative 2 plus 4 over negative 2 plus 1. And let's see. We have negative 2 squared, which is 4. Negative 2 times negative 2 is 4, plus 4 over negative 1. That's negative 12, because 12 over negative 1 is negative 12. Now sometimes we get expressions like this. We have square root here. Let's first, as usual, plug x equals 9. So we get square root x, square root 9 minus 3 over 9 minus 9. And that's square root 9 is 3. 3 minus 3 is 0 over 0. That means that's not a final answer. What should we do in this case? If we have square root like this one in the numerator or the denominator, then we need to rationalize this. How to rationalize this? We multiply by the following expression. We rationalize by multiplying by same square root, but we change the sign between the square root and the other number. And that's called conjugate. So we multiply numerator and denominator by that value. If we have, for example, limit square root x minus 1, then we need to multiply by square root x plus 1 over square root x plus 1, and so on. Now here we have, after multiplying by the conjugate, we get square of the first, which is x, because square root x times square root x is just x, minus 3 times plus 3 is negative 9. In the denominator, we still have x minus 9 times square root x plus 3. And then we simplify. We cancel x minus 9, and we get 1 in the numerator. And then we plug 9 here. We have square root 9 plus 3, and that's 1 over 3 plus 3, which is equal to 1/6. Now let's do a similar problem. Here, problem 8, we plug x equals 4. We get 4 minus 4 over square root 4 minus 2. This is 0 over 0. That means it's not a final answer. What should we do in this case? We multiply by the conjugate, because we have square root in the denominator. So what is the conjugate of this? The conjugate is, we look at the expression that involves square root. It's in the denominator. So we multiply by square root x, but plus 2. That's the conjugate. And we multiply the numerator as well by the same expression. And then we get limit as x goes to 4 of x minus 4 times square root x plus 2. This should be 2. Okay, square root x plus 2, and the denominator we have expression times its conjugate. We get x without the square root. That's square root x times square root x, which is x. Negative 2 times plus 2 is negative 4. And then we simplify. We cancel this with this, and then we plug the value of the limit. We put it here, square root 4 plus 2, that's 2 plus 2, which is equal to 4. Okay, so that's it. This is a good idea. Let me remind you of what we mean by E. E is called Euler constant, and it's a well-known constant, like the pi. Pi is 3.14 something 15, and it can be rounded into to approximate it as 3.14. Here E is about 2.718 something, so we can round it or write it this way, 2.718. So it's a number. That's the most important thing, it's a number.